In my previous video, I've explained how we can understand the logarithm scale in certain graphs. And behind this, actually, the ideas of logarithm plays a very important role. Right? So I make use of this coronavirus cases graph, which is actually found from the Financial Times in around March, okay, and which is a very important and very special graph to us and help us to see in a useful way and some exponential change in the number of cases of coronavirus. And in this video, I'm going to further explain and how generally an exponential curve can be transformed into a straight line and why is it helpful in doing so. And we will use the logarithm and also examine more carefully how the logarithms works. Okay? And I will first start with a more simple graph to talk about the situation. And let's look at the general case of an exponential graph. And let's see the x here still stands for number of days, okay, which will be, let's say 0, 1, 2, 3, 4, and so on. Okay, and then for the y value here, we assume this to be the number of coronavirus cases, okay, accumulated in time, and which is an exponential change and exponential increase, okay? So let's say if we start with 100 as the base value, that means in the day 0, when you start recording, there are 100 cases, right? And it grows by factors of 1.5, which is exaggerated, right? I hope that it won't be so high. But to make it simple, we multiply by 1.5 corresponding to 50% increase, okay? So remember, multiplying by a factor of 1.5, okay, correspond to 1 plus 50%. So it should be a 50% increase each day. And so we raise it to the power x, okay? And that means if you go for one more day, then you multiply one more time this factor 1.5, and you will have this number. Of course, ignore the decimal points. Just look at the whole number part. Then you can imagine the growth will be something like this. Okay, which is very horrible, of course. Okay, in day 12, then you will grow to about 12,000, right? More than 12,000 cases. Now, if of course, if you look at the graph, it will be an exponential graph. Okay, so this is the graph, and what you see in exponential situation. How about if you plot the logarithm of this y value? That means the logarithm of this total number, right, in the middle. So I will write down log of 100 times 1.5 to the power x. Okay, okay. And so be careful, this is the log of the number in the middle. And so that means 100, log 100, you have 2. Or on the other hand, that means 10 to the power 2 becomes 100. Okay. Similarly, 10 to the power 2.176, something like this, you will have 150. So all this column, the third column, will be the logarithm of the middle column, the total number. And you can see that these are the purple points representing the logarithm, which is hardly distinguished because they are so small in this scale. Okay, and okay, let's hide the green point and just concentrate on the purple points, which are the logarithm. Now you can see that the logarithm of the previous values, okay, now lies on a straight line, and it range from 2 to something about 4, because all these are the exponents when the middle number, the total number, is expressed as a power of 10. So when it starts from 2, right, and exponents of 2 means 100, and when it goes up to 3, right, that is just about 1,000, right, because this corresponds to 10 to the power 3, and you can see here 3, okay, and sorry, it is a 6th day. On the 6th day, the number grows to 1,000 something, right? This and the index is at that time is just about 3, and for another 6th day, then at the 12th day, the index or the exponent is 4.11. And when the exponent is 4, it corresponds to 10 to the power 4, okay? So actually this number is originally something bigger than 10,000, so which is found in the table here. Now, so this is how it works. And so by concentrating on exponents, you can see more clearly how the numbers are growing regularly on a straight line. Although originally, right, you don't forget that originally it is actually an exponential curve, right? But sometimes it is easier for us to read if you understand the meaning of exponents or logarithm, and then particularly can help us to easily identify any kind of exponential growth if the points are lying on a straight line, in this case of logarithm. And maybe we can look at a little bit more details about the way these purple points are generated. And in fact, we are actually calculating these values, okay, 100 times 1.5 to the power x, right? But the logarithm. So this red line actually shows continuously, okay, these values. If x is taken to be any values, not just the integers, then there will be any points on this red line, okay? Now, it may be very difficult to read this expression, but if you understand the properties of logarithm, then you will find that it is just the same as the logarithm of 100 plus the logarithm of 1.5 to the power x. And in fact, the power x should be here. Okay, then you can see the correct relation. You can even further simplify it because this log 1.5 to the power x is the same as x times log 1.5. Okay, so I just take it away. Okay, so these two expressions are actually the same, but in the second expression, you can see more clearly why the pattern is linear, because it's just a variable x, which is the day, in our case, in our example here is the number of days, times a constant log 1.5 plus another constant log 100. And log 100 is also the y-intercept of the straight line at the same time, okay? And don't forget that 1.5 is the factor determining the exponential growth, right? So it is a growth based on the factors of 1.5 each day. But in this graph, it is just the constant log 1.5, which is also the slope of this straight line. And this explains why the number of cases of coronavirus, okay, if they're in the exponential curve, and will be transformed into a straight line if you take the logarithm and plot the logarithm against the x value, which is the number of days. Okay, now let's look at maybe a more general case. You can, if you're interested, you can go to my GeoGebra file here to also study this more general case. In this graph, in this page, I put together two graphs in parallel so that you can compare directly. On the left here, you have the original graph and also the number of days and the x-axis and the number of coronavirus cases on the y-axis. I have 2 points marked here, okay, representing and day 10 you have 220 cases, day 16 you have 500 cases, but you can take away the curve, and then maybe you don't know whether it is actually an exponential curve, but you can imagine if it is growing exponentially, what happened to later days like 20, 25, how far will it go? Okay, and how can you tell? For example, if you have a point C, okay, in representing a maybe later case, do you think if it is exponential growth, okay, and then in the day 25, the cases will be 1,000 or more? Would it be 1,400, something like this? Now, it's very difficult to tell whether this 3 points is lying on an exponential curve. But on the other hand, it may be easier if you turn it into logarithm. So on the right, here is another graph. While the vertical axis here represents the logarithm of y, okay, y values on this graph, and if you take the logarithm, it becomes the values on this graph, okay? So this graph plots the logarithm of the y value of the original graph. And you can see that, as we explained earlier, if ABC is lying on a straight line, then this original graph will be exponential growth. So let's have a check. And so this point C is below exponential, and actually at the same time, this point C is this C prime is actually lower than the lines joining A and B. Okay? And so you can see more clearly how they are matching each other, right? Whenever you put a point on the same horizontal exponential graph, then this point here should be on a straight line, okay, through the point A and B in the logarithm graph. And so you can see the relation, which I put down here, okay, corresponding to this relation, y equal to k times c to the power x. You can even find out k and c, that means the constant here in this straight line graph, because once you plot the logarithm of the values or in this graph, based on the slope, you can find out log c. And based on the y-intercept, you can find out log k, okay? In that way, you can also find out k and c and go back to our original graph to find out what should be the curve passing through A and B, right? So this is shown here. And so in this case, the y-intercept is 1.75 and the slope is 0.06, right? Correspondingly, the factor is 1.15, okay? The growth factor is 1.15 and the constant at the beginning is 56. That means around here, 56 case at the beginning. Now you can even do other comparison. If you pick up 2 other points on this graph, okay, you may wonder, how about in another city, if you have this situation in day 10, you have 600 cases, and then day 15, you have 1,000 cases. Do you think it is growing more rapidly than the original one or less rapidly? How can you see? In the exponential situation, it's not that easy to imagine or estimate, right? But if you put it back into the straight line graph here, or in the logarithm case, then you may be able to distinguish it, right, more clearly. Now you can see this red line is not so steep as the green line. So correspondingly, this graph, right, has a factor 1.11, which is less than 1.15, okay? So these two curves seems to be very close to each other, but the straight line graph here tells you a different slope, which is much easier to distinguish, right? So you can try to check it. For example, when will they be parallel? Okay, that means when will these two factors be the same? So this can also be compared directly. And this is the very important use of the logarithm, in this case, telling you how the original values are behaving exponentially or not. Now, finally, if you want to actually read carefully the original values of y on the same graph, you can do this transformation, right, on this axis. Right? Don't forget that if you see 2 on the log scale, that means the original values is 100. If you see 3 on the log scale, the original values is 1,000. Okay, and this is also the way the original graph that I shared with you, okay, and show this. Okay, remember this original graph from Financial Times, they don't show the logarithm directly, right? In fact, they show the original value represented by the logarithm, right? Although the positions of these values on the line is put according to the logarithms of the values, okay? So maybe you can make use of these few graphs to help you to understand more carefully how the logarithms work and why it's useful in many of our cases, right, where we are reading scales like this or reading a range of numbers which is very big and difficult to comprehend the ratios among them, right, in an easy way. So I hope that you can gain something useful from this videos. Okay, bye-bye.